All right, we need a little crash course on complex numbers for linear. My hope is that you've seen complex numbers just a little bit. You've probably seen them someplace in this course, maybe in differential equations if you're in there. Could have seen them in a pre-calculus class or an algebra class. Like, there's some options. Um, if you have seen these and you get bored watching this video, please check out the end of the video to make sure that you actually get everything that I'm going to say, because there are probably going to be a few things that weren't covered in any of the other times you've seen complex numbers. So for our start, I'm going to assume that I've got a complex number z that's in the complex plane. That's how I denote complex numbers here. And I want you to kind of think about the complex plane as being a two-dimensional real vector space with vector multiplication. This is a bit bizarre. I've probably told you a bunch of times that you can't multiply vectors. Well, generally speaking, you can't. In the complex numbers, you can. This multiplication is not a dot product. So this is not just the dot product. So what I mean by multiplication in this sense is I'm going to be able to take two complex numbers, I'm going to multiply them together, and I'm going to get another complex number. So that's something like, i.e., z times w is a number in C. And I'm going to avoid using this dot here because we're going to have some stuff with dots. Okay, so that's z times w is a vector in C. All right, so let's get some building blocks out. So for the sake of this, I'm going to assume that z is a real part and an imaginary part. So that's z is a real number a plus an imaginary number b. So that's a and b, or sorry, a real number a and a real number b. And because I'm multiplying b by I, that's going to be a purely imaginary part. So terminology wise here, a is going to be the real part, and b, just b, is the imaginary part. And the I just tells you which bit is which, essentially. Okay, so if I'm going to like say, I don't know, let's start with something simple. Let's scale a complex number. So if k is a number in R, then kz is going to be ka plus kbi. That's it. Just scales the pieces. That works, by the way, this kind of same way that you might think about vectors, right? So if I'm thinking about z in terms of a two-dimensional vector, I might be thinking about it as ab, right? If I scale z, right, I get out a vector that looks like ka kb. So that's kind of working as expected. Most things here are going to work as expected. I'm going to raise a couple. Don't worry, I'll throw a big red warning around them or something for the ones that are a little different. So that's kind of scalar multiplication. I've also got something like vector addition. So if I'm adding z and w, that's going to be like taking a complex number a plus bi. I guess I should throw what w is here. So I'm going to assume that w is x plus yi. We might think about that as the vector xy if we were in R2. So that one's kind of, we're thinking about that in R2. Here we're thinking about this in R2. Oops. Okay. So if I'm going to take z and add w, I'm going to take a plus bi and add x plus yi. That's going to give me a plus x. That's my new real part. And b plus y times I. That's my new imaginary part. You might notice that works exactly the same way if we added the a plus b and xy. This is all basically same as scalar, or as the two-dimensional real vectors would be. This is where we get to different things. So zw is not the dot product. This is a plus bi times x plus yi. And the only real thing here that we're going to need to know is that when you multiply I by itself, you get negative 1. So I'm going to distribute this a little bit. I'm going to get ax plus ayi plus bxi plus byi squared. And so then I'm going to go, all right, let's see. So I guess when I combine things here, the I squared, that's going to end up being -1. So my real part is going to be ax minus by. And then I'm going to be adding to that my imaginary part, which is going to be ay plus bx. And we're multiplying by I here. So that's how multiplication works. Please note, this is not the same as if you took the dot product, right? If I took the dot product between these two, my kind of two real vectors that I'm thinking, I'd get ax plus by. That brings up a kind of a counterintuitive thing, but to get there, I need this other operation. So here's my other operation. This is called a complex conjugate. And this is actually going to cause me to drop those little vector hats that I've been kind of drawing all semester to remind you which things are vectors. So here I'm taking a complex number and I'm doing what's called a complex conjugate. So this is the complex conjugate. You may have seen these at some point in like an algebra class or something. There was a conjugate of like things with a square root in them or something. I'm just going to write it down here. It's just a minus bi. So it's the same real part, and then the imaginary part just flips sign. That's it. Easy peasy. So let me talk about multiplying a vector z by itself. So if I multiply a vector z by itself, you might think this would give you something that's like a little bit similar to a dot product or something. As it turns out, it's kind of different. So a plus bi multiplied by a plus bi, it's going to give me a squared. That part feels a little familiar. But then I got 2abi, and then I got a minus b squared out of this. So if this were a dot producty thing, I'd be kind of expecting something like a squared plus b squared. That's actually how I would think about the length, right? So this isn't the magnitude of z squared. So got to be careful with this. What is the magnitude of z squared is z times z conjugate. So this is going to be a plus bi times a minus bi. And so I'm going to get a squared. I'll get minus abi plus abi minus b squared I squared. And so that's going to end up being a squared plus b squared, which is the magnitude of z squared. So I'm going to call this absolute value when we're in the one-dimensional case. In the two-dimensional case, I'll add those norm bars. Or in the multi-dimensional case, we'll add the norm bars. But what this means, right, is that I have to be just a little bit careful. If I'm thinking about z as a vector, when I dot product it with itself, there could be some issues, right? So as long as you've fully switched to the R2 case, you can go ahead and do this. This is going to become a little bit of an issue when we have complex vectors, right? So a vector where the entries are complex numbers. So let's see. Let's write that down a little bit. So this is, by the way, where you could hop back in if you kind of understood about complex numbers, because this is going to be a different thing. So we're going to have complex vectors. So I'm going to think about a vector x. Should add a bit of a warning here. I'll be writing x as a vector. So I'm going to be writing x and x conjugate instead of x with a vector hat and x with a vector hat's conjugate. So the issue here is I'm thinking about a vector x that's going to be made out of a complex number z and a complex number w. Right, so I'm thinking here this is an entry in C2, which I could also think of as R4, right? So let me say, actually, this isn't I'm thinking of this. This is a vector in C2, which I might think of as a vector in R4. So if I was thinking about that as a vector in R4, right, I'd be thinking about A plus BI and X plus YI. And I might think about that as A, B, X, Y. Right, that's me essentially thinking this first two coordinate or this first one complex coordinate is kind of the same thing as a two-dimensional real coordinate. Should be noted this thing has some advantages over this guy, so we tend to leave these as two-dimensional complex vectors. But if you need to think about them as four-dimensional real vectors, you kind of can. Okay, so here's the like operations that are chill. So if I take a scalar and multiply by a vector x, this is going to be my scalar k times this vector that's z in the first coordinate, w in the second. That's going to be exactly what you'd think it is. It's kz, kw. This works exactly the way it did up above, right? I'm just going to distribute the k through the components of z and through the components of w. Great. Easy peasy. This all kind of basically works. If I wanted to add vectors, I would do it exactly the same way, right? I'd just add coordinate wise, fine. Like that operation's real chill. The issue here is when I'm thinking about doing a dot product. So I'm going to raise a fat warning here. Dot product is a bit different. Like if I want a dot product that works the way I think it ought to, I'm going to need things to be a little bit different. For this, I'm gonna play with an example for a second. So here's my example. If x is the vector I and 1, then it seems to me that I ought to be able to do something like x dotted with x ought to be just x transpose. Let me actually write that down. Ought to be something like x transpose x, right? If that were the case, I'd get I1 times I and 1. I'd pick this vector up, I'd turn it sideways and drop it onto that vector. I'd get I squared plus 1, which would be 0. That would indicate to me that this vector is like perpendicular to itself. And that's kind of, well, that's kind of fucked, frankly. So this is not, in fact, how dot products work. So we have to say, no. That can't be the case if things are to make sense. So we're gonna refine this. So we're gonna define if I'm taking a vector x dotted with a vector y, whoops, in C2, right? So let me rephrase that. With x and y are two-dimensional complex vectors. The way I'm going to do this is I'm going to say x dotted with y is x transpose times y conjugate. So if I try this out with my example, this is going to be, I'm going to take x is I and 1, and I'm going to try to calculate x dotted with x. So this is going to be x transpose times x conjugate. So the way that's going to work is I'm going to leave my transpose, so that's going to be an I and a 1. And then here I need to take I and 1, but I need to conjugate this vector. So what that's going to do is I'm going to conjugate the pieces. So that's going to be the vector I and 1 times the vector minus I and 1. And when I do this multiplication, I'm going to get negative I squared plus 1 squared. Which is going to give me, well, negative I squared. I squared is negative 1, so this is going to give me 2. So this would tell me that the magnitude of I and 1 is the square root of 2. And that jives with my intuition. Because my intuition is I'm thinking about this vector as I and 1 as 0 plus 1I and 1 plus 0I, which I could think of in a four-dimensional real context as no real things, one complex thing, no real thing. One real thing, no complex thing. And this vector is the square root of 2 long. So I feel like I've got a thing here. This is how dot products have to work if they're to make sense with my usual. So if I need the length of a vector in a complex sense, I don't do x transpose x. I do x transpose x conjugate. So you have to remember that conjugate. It's kind of that same thing from up here, that if I wanted the length of a vector, I actually need to multiply z by z conjugate. Alternatively, you can shift it to R4 and use your usual square everything and add it all up. That'll also actually work here. So either way is totally fine. I think that's what I need you guys to have. Oh, one thing. Last thing. Thing of note. So note this. If suggestively lambda is a real number, what that means, right, is that it looks like lambda plus 0I. Right? That makes sense? So I can essentially include real numbers into complex numbers. And then it is enough. So lambda is in R is equivalent to lambda equals lambda conjugate. So if I have a complex number that is its own conjugate, then that number is in fact real. This is going to be relatively clutch later. So thanks for watching. Remember this little warning about the dot product. It's not super intuitive. Much appreciated on the time today, guys. I will see you all later.